My boat got put in my leg.
Well, let's kind of get started then. So I'm going to start by taking questions from this most recent homework 3, if anybody has any. Okay, fair enough. On we go then.
Wait, is that one that you just signed? Can you do number 2?
Which number 2? There's 2 numbers.
Is it like the first number 2? Not the graph.
Okay. So write a model. This is a radioactive decay situation, so I'm going to use that model with the E in it. So the initial amount is 100 grams. The value for R, this is tricky because it's decay and a half-life. Since it's decay, it's got to be negative. And if it's a half-life, half is 0.5. T. But in the case here, T is the number of half-lives. It's not just raw time. So part B says how much radon is remaining after 200 minutes. So the first thing I'm going to do is convert that 200 minutes into half-lives. And then I'll go ahead and plug that into my model that we wrote earlier. So I'd have about 2.99 grams left. And then it says how or when would you have 10 grams remaining? So this is a all in the calculator question. We're going to do this by graphing. So 10 is what I'm looking to get to. And then my decay model, 100 times e to the negative 0.5 times x. We'll set our window. So this is time. We know here we had less than 10 grams remaining here when we did this. So I know that it's going to be somewhere between 0 and 7. So 0 to 10 is going to be fine. The maximum amount that I could have was 100, and the minimum, well, it's decay, so it can get down to 0 grams. Right? Eventually all of it could be gone. So there's my 10 gram, there's my decay. This is the time that I'm interested in right here. So second and trace, we'll pick the intersect command, and then enter, enter, enter. I get 4.6. But remember that the T is half-lives. So I need to convert that into time because it's asking for when. So I'll just take that 4.6 and multiply it by the half-life, which is 28.5, to get about 131.1 minutes.
So what did you just multiply it by?
The half-life. You're welcome. So a couple of tricky pieces in there. You needed to get the R right on your half-life. And and then needed to recognize that the t in your model was going to be in terms of half-lives and not minutes. Okay. Today, then, we're going to talk about logarithms. So this is the other half of this chapter. So what a logarithm is going to help us describe is the value of an exponent. So for example, if I have 2 to the x is equal to 4, what is my value for x there? 2, right? Because 2 squared is 4. And what if I have 2 to the x is equal to 8? What's my value of x got to be there? 3, okay. But what if I have 2 to the x is equal to 6? Well, let's make a guess here. What do you think that x could be? You mean 2.5? Yeah, 2.5 is maybe a decent guess, right? 6 is halfway between 4 and 8, and 2.5 is halfway between 2 and 3. Maybe it's 2.5. Let's check. Oh, not big enough. So maybe we try 2.75. No, that's too big. Okay. Maybe we try 2.6. Still too big. So maybe we try 2.55. Not quite big enough. And we could kind of keep on guessing and checking this. And we'd be able to get more and more decimals. So maybe 2.58, not quite there. But if I go to 2.59, that's too much. So it's 2.58 something, maybe 585. That's still too big. So maybe we do 584. Not big enough, so I need to add a little bit more on. So maybe it's 5845. Not big enough. And maybe 5846. Not big enough. Maybe 5847. Not big enough. Maybe 5848. Not big enough. Okay, maybe 5849. Not big enough, but 5845 was too big. Remember, we checked that already. So we must just need some more at the end of that. So it must be 5849 something. Well, ending in 5 isn't enough. And we can keep going and doing this and keep guessing and checking. Do you think we're ever going to get exactly 6, though? No. It seems like that decimal is going to keep on going and going and going, right? If I look at the pattern of the numbers in that decimal, does it seem like there's a pattern in that number? 2.58496 something. We're still kind of working on that last digit there, or that end digit. It's big. What do you guys think? Do you You think there's going to be a repeating pattern in that decimal there somewhere? Doesn't seem like it, right? So nothing has found its way yet. What do you call a number that its decimal goes on forever and there's no pattern in the decimal? We call that irrational. Good. So this was about 2.5. Stupid thing. So we got these new computers or whatever, which is lovely. I love them. But like every once in a while, like one note just kind of like freezes and just doesn't ever come back. And the only thing I've found to get it to come back is just to like end task on the program and have it and then restart it, which is kind of a hassle. So we got like 2.58. But we've established that this is like an irrational number. So whenever we've encountered an irrational number like this, we don't ever really default to a decimal approximation, right? We give it a name. So like in geometry, you guys encountered pi. We use the symbol pi. Last lesson, we encountered this letter, or this number e, we gave it a name, right? Prior to this, we encountered irrational numbers like the square root of 2, the square root of 3, the square root of 5. Again, we don't use the decimal, we just call it square root of 2, right? We're going to do the same thing here. We're going to call this number log base 2 of 6. So this is basically describing the power of 2 that equals 6. So that's the name we're going to give to that number. Everybody okay with that idea? So again, when we talk about logarithm of something, we're just talking about a number. It's just a number. It's usually a big kooky decimal that we just don't want to have to write down. Similar to what we did with square roots or cube roots or all those other irrational numbers that we dealt with last chapter. So this comes to give us our definition for a logarithm. So it is if we have some exponential equation, b to the x is equal to y. That's the same thing as saying x equals log base b of 1. So this is like our exponential form, and this is like our logarithmic form. And we can kind of go back and forth between them. So for example, we can use this definition to evaluate logarithms. So if I want to know log base 2 of 8, I can convert this into the x. I can imagine that this is equal to x, and convert this into the exponential form. So the b is the subscript, so that's going to be the base of my exponential. Is it doing this all the time? I thought we were done with this. Yesterday everything worked so smoothly. So I'm going to have 2. What the logarithm equals is the exponent for my exponential, so that's x. And the number inside my logarithm is what the exponential is going to equal. So we're left with like 2 to the x is equal to 8. And hey, we know what that is. And just x is 3. So we can say log base 2 of 8 is just equals 3. Everybody okay there? They could be kind of sneaky. So what if we did log base 4 of 1/2? Well, we'll start it the same way, right? We'll pretend that's equal to x. So what that means is 4 to the x is equal to 1/2. And there, oh boy, that still doesn't help me a whole lot. Here's the trick, is I'm going to try to rewrite 4 and 1/2 so that they have the same exponent base. So I notice 4 is a power of 2, and 1/2 is also a power of 2. You gotta be joking me. I've done like nothing. And 1/2 is just 2 to the negative 1. Oops. Everybody okay with that? Remember we had that exponent rule. Oops. That's what I used to get 1/2 is equal to 2 to the negative 1, right? Okay. So I have an exponent of an exponent. Those can multiply. And the only way that this equation is going to be equal now, since the bases are the same, is if the exponents are also the same, right? That stands to reason. So x is negative 1. And if we wanted to, we could check that, right? 4 to the negative 1/2 is 1/2, right? Which is what we're looking for. Everybody okay there? So that's kind of worst case scenarios. You have a situation like that. But the trick is always just going to be to find a way to rewrite it so that they have the same exponent base. And then you can just set the exponents equal to each other and finagle it from there if it's not a sight one. Now, not all logarithms we can do without a calculator. So we saw earlier log base 2 of 6. That was something that when we tried to do it by hand, there's not going to be a way to or a way for us to do it by hand. I mean, there's a way to do it by hand, but it's beyond the scope of this class. So what we'll do is we can use our calculator. So to type this into our calculator, we're going to press the math button and go down to the very end of that math menu, and you should see a command called log base. If I select that command, it allows me to type in this to look exactly like it does on my sheet of paper. So I put the 2 in the base and the 6 in the argument. And I press enter and I get about 2.85 or 85. You're joking. This is like 3 times in a minute. I just want to take it and break it over my knee.
I can do it if you want.
You know, well, we couldn't start OneNote the last time we tried. What do you want us to do? Start normally, delete the cache. Delete the cache. It's fine. We don't have any open notebooks. So I have to reopen all these notebooks. Cool. Thanks. Goofuses. This is, I gotta say, I love this. Technology is awesome. The old ones were having difficulty doing everything that we needed to do all at the same time. So like if you want to run a Zoom call and do something else and do something else all at the same time, they just weren't really up to snuff on that. So we got new ones. I think I assume we're getting the new ones now is because there was a grant that was going to run out, so there was like a you know, like you had to use the money or you're going to lose it kind of thing. But we got new computers. Is it all gone? Where are all my notes? You stupid machine. That makes me so angry. Alright, well, I don't even remember what we were doing. So there's some stuff. And then, what were we doing? We're like log base 2 of 6, right? I just didn't get a chance to write down the answer. And it's frozen again. How am I supposed to be expected to do my job? Well, let's delete the settings this time. Since deleting the cache didn't really work. Oh look, some notes came back, but not the ones that I wanted. Yes.
Can you re-show how you did that on the calculator?
So I press the math button, go down to the bottom to grab the log base command, and then just put the 2 and the 6. Press enter. It's pretty easy. So a couple facts about logarithms. No. Why? How am I supposed to, like, what are we supposed to do here? This is so bad right now. And this isn't like it's using a, like, where are all the resources? Why is all this stuff freezing? I'm not even, like, 50% of the CPU isn't used. Why is it freezing on me? I just don't get it. I just don't understand it. I really don't. Right? Like, it's not that hard. I'm not using that much stuff. Why is it freezing all the time? By the time I rewrite whatever I had written last, I'll probably freeze again. So first things first, you can't take the logarithm of non-positive numbers. So if it's 0 or negative, no bueno there. Are you okay with that idea? Just to kind of illustrate that to you, if I did log base 2 of negative 6, I get an error. It says non-real answer as my error. Okay? So if that happens, that's all that's happening. You probably either made an algebraic mistake and weren't supposed to get a negative value, or you just ran into a problem that you just can't do. Now there is complex answers for some of these, but that's beyond the scope of our class. We're not going to worry about that. Okay? We're just going to go with, say, we're not going to handle it, and we're not going to do the i's for the logs because it's more complicated than we need to handle in a high school classroom like this. Next one up is log base b of 1 is always going to equal 0. If you think about that for a moment, if I use my definition of a logarithm, that's basically just saying b to the 0 is equal to 1, which was a property for exponentials, right? So no surprise there. It's basically the logarithmic version of that property. Okay. Everybody feel happy with that? NVD there. And the third log fact that I have is log base b of b is equal to 1. Again, if we think about using our definition, that's equivalent to saying b to the first is equal to b, which is like, no doy. So sure, of course, b to the log of b, or log base b of b is 1. Sure. No big deal. So those are some basic properties there. So we do have 2 special logarithms that we have a special notation for. So the first one is called the common logarithm. And it's frozen again. I just don't get it, guys. It is a bad day. It's turning into one. It really is. my first one is the common logarithm. And that common logarithm is log base 10. But instead of writing log base 10, we write log with no subscript at all. Critically important that you memorize the fact that log with no subscript means log base 10. You're going to see that happen frequently, and if you can't remember that, it's going to cause all kinds of problems later on. I want to point out to you on your calculator that the regular, or this common log, is built in as a button on the home of our calculator here, right next to the 7. So if I wanted to do log of 7, I get that number, which basically says 10 to that power should give me 7, which is what I demonstrated there on the calculator, right? The second of these special logarithms is called the natural logarithm. And that's log base e. So instead of writing log base e, we write ln. Which again, if you look at your calculator, right underneath the log button is the ln button. So say I wanted to do ln of 7. So that's that number. What that says then is e to that number, 1.9 and change, is equal to 7. Everybody okay with that? So again, critically important that you remember that the base for ln is e. So those things will come up quite frequently, and if you don't have it memorized, it's going to be a problem. I want to take a minute here and talk about how you're writing things on your sheet of paper. So I want to point out to you, you've noticed that when I've written my logarithms, I'm using cursive. I would really encourage you to do the same thing, is to write your logarithms with a script instead of printed. Because I've seen many times students write log, log of 7, and somewhere along the lines that turns into 10g times 7 and turns into like 70g. And you're looking at that like, that's weird, why would somebody do that? Lots of people do that every year because they can't tell the difference between their 1 and O, or their ln O and a 1 and 0. So my suggestion to you to avoid that is try to use cursive to write your logarithms. When you write log or ln, to write them in cursive so you don't make that same kind of mistake later on. It's easy to get bogged down in a complicated problem and go back and look at something and be like, oh, that's 10g. I mean, I haven't done it, but I've seen it happen lots of times. So I wanted to just kind of take a minute and talk about that, since we're talking about notations right now. Okay. Everybody still doing okay? So throughout our mathematics education, whenever we've learned a new operation, shortly thereafter we learn about its inverse operation. So like when we learned addition, shortly after that we learn about subtraction, the way to undo addition. When we learned about multiplication, shortly after that we learned about division. When we learned about squaring, shortly thereafter we learned about square roots. Or if we wanted to talk about exponents in general, shortly thereafter we learned about the nth root. This now, with the logarithm, completes another pair of inverse operations. So we have our exponent base pairs with our logarithm. So the big takeaway here, and maybe the most important idea from this first introduction, is that log base b cancels exponent base b, and then vice versa, that exponent base b cancels log base b. So just to kind of show you what I mean by this symbolically, because again, we write the words down and then, you write symbols on a paper, and oftentimes it's hard to connect the two ideas together. So let's do symbolically what this is saying right afterwards. So what this says is that if I have like log base 2 of 2 to the third, the log base 2 is going to cancel with the exponent base 2, and it leaves just the 3. Note here that 2 to the third is 8, and we established earlier that like 2 to the x equals 8 implies that x is 3, right? It's basically doing the same thing that we did before. It's just kind of shortcutting around a little bit of the algebra. But this is not a new notion that I just established. We were doing this earlier. We were just using that definition to kind of weasel around with things. This is maybe a little bit more convenient way of conceptualizing, though. I want to take a minute and just talk a little bit about how to interpret the notation that you're seeing here. So remember that these parentheses here are not indicating multiplication. This isn't log base 2 times 2 to the third, right? It's like, just like sine of 45 isn't sine times 45. Sine isn't a number, it's not a quantity, it's an operation. Log base 2 is not a number or a quantity, it's an operation. It'd be like saying, oh, I'm going to multiply by square root symbol, which doesn't make a lot of sense. Or I'm going to multiply by addition sign. That doesn't, that's a bunch of gobbledygook, right? Okay. The other side, then, we said that log, or the exponent base b cancels log base b. So you're left with just whatever is in the exponent. And again, I want to make clear that that is an exponent base, and that's not the same thing as a coefficient. Everybody's clear on that? So again, it's an easy mistake to make if you're getting kind of messy. I try very hard when I'm writing to write my exponent bases so that they're a little bit bigger, and the thing in my exponent is a little bit smaller, so I can keep it straight between multiplication and an exponent base. Strongly encourage you to do the same thing. It's really easy to kind of get a little sloppy with that on your sheet of paper. Next thing you know, your exponent base is turned into multiplication, and now you're doing all kinds of stuff there. Okay? So, last thing I want to talk about here in this lesson is finding the inverse function. So this was something that we did in first semester, and we're kind of just circling back to now. So we'll start with an easy first semester example, and then we'll do another example using this latest stuff we've been talking about. But right now, what we're doing, this example has nothing to do with logs or exponentials or anything else. So the idea when we're finding an inverse function is we want to get the x by itself, and then we switch the names of our variables. So the x becomes y, and y becomes x. So if I'm trying to get the x by itself, what would be the first thing I'd want to do in this example? Subtract 6 from both sides. Good. And remember that you can't subtract a number from a variable, so we'll just write that minus 6 right next to the y. Then what should I do next? Divide by 5. Good. Divide both sides by 5. And again, I can't divide a number and a variable, so I'm just going to write the whole thing. Now the x is by itself, so my last step then would be to swap the x and the y, and that would be my inverse function. Everybody's okay with that? So let's say we want to do y equals 5 times, what is that letter? That's supposed to be a 6. 5 times 2 to the x is equal, or plus 6. First things first. Can I do 5 times 2 to the x is equal to 10 to the x? Is that okay? Nope. Never okay to do that. And you're like, wait a minute, Mr. Booth, we've done a bunch of stuff like that all over the place. No. You have to be quite careful here. Frozen again. Maybe not. It was close. So we had two situations, right? That we can on how we can multiply things together. If the exponent bases are the same, we can multiply things together by adding the exponents. Well, clearly 5 and 2 are not the same exponent base, so we can't do that. The other situation we had was if the exponent is the same, we can multiply the bases together and keep the exponent the same. Well, the exponent is definitely not the same on 5 to the first and 2 to the x, so we can't multiply those things together. You need to do one of these two things to be able to multiply something together. Everybody's okay? Just wanted to reiterate that. Again, that's a common mistake I see students make. I want to make sure that we're addressing that now and kind of thoroughly explaining why you can't do that. Okay, so if we can't multiply the 2 and the 5 together, what should I do first? Subtract 6 from both sides. Yes. Yes. You're welcome. Did it again. Has anybody kept count? How many times have I done this now? 6. So I'm going like over almost 1 time every 5 minutes here. Or more than 1 time every 5 minutes, I guess. Yeah. I couldn't even do it, it just immediately froze. That's such a... Okay, here comes number... Is this number 7 or 8 now? 7. I'm going to try doing that. And see if that helps make a difference. Why does it still say it's syncing? It should be syncing anymore. I told it to stop. Okay. Alright, so I subtracted 6 from both sides. What should I do next? Divide by 5, right? Sure did. Why not? Sure. No problem. And again, I would understand if like this was the CPU percentage on the OneNote was going like crazy. But like OneNote's not even doing anything. I don't understand why it's, you know, like I can't do anything with it. It thinks it's doing things when I'm trying to press something on it. And it's not like I'm going a million miles an hour here or something where it makes sense that it was getting all laggy. Okay. So we divided both sides by 5, right? Now to get this x by itself, we still got to get rid of this 2. How can I get rid of that 2? What's going to cancel out that 2?
Divide.
Well, is the 2 being multiplied to the x? No. So dividing isn't what we want, although that's the natural first guess.
Multiply both sides by 2.
Multiplying both sides, well, is 2 being divided to the x? No. So multiplication's not what we want.
Square root. What do you call it?
Square root won't work because it's not going to get the x out of the exponent, right? It would get rid of an exponent, but the x is what we want the x to be there. We want to get rid of the 2 instead. What we need, the 2 is an exponent base, right? What cancels an exponent base? a logarithm. So that's what we're going to do to both sides. Which logarithm are we going to use? I want the log with the same base as my exponential, so I want log base 2. Log base 2 cancels exponent base 2. And we're left with just the x. And then we just switch the names and we're done, right? Everybody okay there? Let's do another. So let's say we have 3 times the natural log of x minus 1 and the plus 4. What should we do first? Subtract 4. Very good. And then what should we do? Divide both sides by 3. Okay. And then how are we going to get rid of that natural log there? What cancels a logarithm? So an exponent base is going to cancel a logarithm, right? So in our case, what is the base on our logarithm? What's the base on ln? It's not 1. It's e. Remember, this was one of these 2 notations that I said was going to be super important that we had to memorize and remember what the bases were for these 2 special situations. So for ln, the base is e. For the common log, the base is 10. Got to make sure you remember that, because when we get to doing problems like this, you are in a load of trouble if you don't remember that. Okay, so now I'm going to do exponent base e to both sides. And I'm going to draw my exponent base comically large. Again, the reason I'm doing that is I want to not be confused about whether I'm multiplying by both sides by e or it's an exponent base of e to both sides. So I'm going to write it comically large. I know that seems rather silly, but that's, in my experience, this helps, especially if you're going back to look at your notes, that you're not confused at multiplication versus an exponent base. So that E is going to cancel the ln. So we have then E y minus 4 over 3 equals, and then everything in the logarithm is still left, so I have x minus 1. So we still have a little bit more to do to get the x by itself, right? What else do I still need to do? Yeah, we're just going to add 1 to both sides. Pretty good. And then we're all set, right? We can just swap our variables, and we're done with those. You guys feel pretty good about that? So for this homework, I have a couple of different kinds of problems I'm going to ask you to do. So a couple of problems I'm just going to ask you to use your calculator to evaluate. So just practice using your calculator. Round your answers to 3 decimal places, no big deal. Here we're just going to be converting between the forms using the definition. So here's an exponential form that I want you to write as a logarithmic, and here's a logarithmic that I want you to write as an exponential. Right, we did that in the examples. Here's some simplify the expression without your calculator. So some of these should be easy, and some of them will probably get a little bit challenging. And then the last questions are write the inverse for the function. So just like what we just got done doing. So nothing crazy. All of the things we worked on, we added examples. We did some examples of. I'm going to stop here because this tends to be kind of a challenging concept for students. I don't want to go too far too fast. I want to give this a chance to sink in before tacking more onto it. But just to let